All right, good morning, everyone. Really wonderful to see everybody here. A talk and event like this is really the most rewarding, inspiring. Not only we have a wonderful speaker, really inspiring talk, also to see a lot of people from Columbia, from different school, faculty, students, staff, and also from industry and a partner from New York City. So welcome. So I'm Shifu Chen, the Dean of Columbia Engineering School, and over the years, Engineering School has really set up a lot of collaboration with industry across the school. We were just talking to Tom and faculty how interdisciplinary the school has become and how our student has opportunity to listen to the talk like today and also take courses and research opportunity across different programs. So today we welcome you to this Tech CEO series. And we started a Tech CEO lecture series a few years ago, maybe 2 years ago. And the vision is we have so successful, inspiring leader after the education from Columbia or from other school, and then take the step to the career in the tech field. And being a leader in the tech field, not only you have to have a strong foundation and successful vision achievement in technology field, also you have a strong leadership and you have a strong vision and also your background and also your expertise in interconnecting and integrating your technical expertise with different areas. And that's what we're so proud of the so-called core curriculum or interdisciplinary education for our students here, for our faculty, what we are pursuing our efforts here. So in the last 2 years, we have leaders from company working on sustainable building construction, working on biomechanics in entrepreneurship. Later this year, we have Dean Kamen, who is leading the creation of the national first robotics program, will be coming here. But the most exciting thing is today's speaker, Tom Caulfield, GlobalFoundries, the CEO and the chair, and he will be discussing the importance of a semiconductor in the global economy. As we all know, semiconductor is the driving force, right, in the past few decades that really transforming the society and the industry. And going forward is also going to play a key role in transforming many different fields, including AI, edge computing, consumer electronics, medicine, climate, sustainability, many fields. So he will give us a picture of the global semiconductor landscape and share the challenges and opportunity ahead of us. He has been the president and CEO of GlobalFoundries since 2018. And one of the most exciting achievements he led the company IPO in 2021, which was the largest semiconductor IPO of NASDAQ in that year. He joined the company in 2014 as a senior vice president and general manager of the Fab 8 facility. I think we'll know more about the Fab 8 hopefully later. And previously, he served as a president CEO of Sora and Osra and has a senior role in Novellus System and IBM. And most important one is he's a proud alum of Columbia Engineering. He received undergraduate, Master of Science, and doctorate degree in Material Science Engineering from our school in 1982, 84, and 86, 3 degrees. And even more exciting, Sandra is here, that his wife, he received an undergraduate degree, master degree, and another degree called MET, right? Engineering of in metallurgy in 84 and 86. And now all this material science, mining, metallurgy is coming back, become a very vital part of the school as we are seeing today. So I think without further ado, we're just so excited to have Tom and Sandra coming back to see us on Morningside campus. I share with them our expansion plan to Manhattanville. So next time we will host you a talk in the Manhattanville campus. So let's welcome Tom and Sandra. And Tom is with us.
So I'm not going to talk so much about the economics of our industry. I mean, we're in a digital age. The issue about semiconductors is it doesn't get enough credit for how much it is the digital age. It's the core of everything we do. What I'd like to do is give you a little bit of a perspective on the history of our industry, a little bit about what the challenges and what we're going to do about it, and then the role of AI and how semiconductors is going to fuel the AI revolution. So without that, we have a lot of material to go through. Buckle up and let's get it going. Which one of these? This one. So when I went to school, by the way, that's how we learned. chalk on board. I'm not sure if any of you recognize that, but let's start with the basics. This is the first transistor, solid state transistor in 1947. This was the thing that began to replace vacuum tubes. And there they are, Bardeen, Shockley, and Bratton. They won the Nobel Prize or in right across the river in Bell Labs for this innovation. So we start with that transistor. It becomes a single transistor for commercialization, replace the vacuum tube. By 1971, we created integrated circuits. And then today we have what we call very large scale integrated circuits. Many designs, single chips have 720 billion transistors on them. By the way, they're not one transistor. There's probably 150 different types of transistors in any given design. And how do we make them? We make them on what we call wafers. We started 5-inch, 6-inch. Today, 300 millimeter or 12 inches is how we produce semiconductors today. On any given wafer, depending on the complexity of design, you could have 10,000 chips, maybe 400 chips if you're a NVIDIA graphics processor for AI. So what's been the kind of the hallmark or the attribute of the semiconductor industry that has made it different than any other industry? It's the pace of innovation, something we call Moore's Law. Very simple. Every 2 years, you double the capability of a technology. So let's do some math. It's really a law of compounding. In 1965, we could put a transistor count per square at 100. So 100 transistors. 52 years later of Moore's Law is 26 cycles. Put 2 to the 26, you got 100 million improvement from 1965. It's incredible pace of innovation. We'll talk about what it's done to the industry and applications. But here's why Moore's Law was usually important, because it gave us 3 things. The first thing outpaced all the others. If you shrunk the transistor every 2 years, you either got twice as much technology in the same square size of semiconductor, or you got half the cost pretty much of a transistor. So you get this amazing amount of productivity that allowed new applications to come about. By the way, you also got improved transistor performance, so for speed. And something that's very important today is you get lower power per transistor. The smaller the transistor, the less power to switch them. So when you hear about Moore's Law, the biggest thing was always about the shrink or scaling, which is on the far left, which is the economic part of Moore's Law. But performance and power are equally part of that. And later on, we'll come back to talk a little bit about where we are on that journey and what we're going to do about it. So let's look at another industry and give a sense of the relative compare. If the auto industry innovated at the same pace the semiconductor industry has over the last 50 years, this is what it would look like. A Rolls Royce would cost $40, and you could circle the globe 8 times on a gallon of gas in a car. This is just perspective on how much innovation has been in our industry. Again, we're going to come back to this theme a little bit later on. So, but what did the industry do? The auto industry just didn't say we're done. They found other ways to innovate. And a common theme for all of you should be, anytime you get stuck where you think innovation is monolithic or linear, right, you're thinking about the problem wrong. You have to find broader ways to innovate. So the auto industry, what do? We put driver assistant technology, lane departure warning, self-driving cars, collision detection, nav systems. We've created a better experience, a safer experience through different levels of innovation. By the way, it's like everything else in the world, it's all been enabled by semiconductors, but nonetheless, innovation for the application. So let's get back to where the story begins. There's your transistor. In the 50s and early 60s, single transistors enabled the first hearing aids, transistor radios. I'm old enough to have had one of those. I see you shaking. You look like we're in the same class, right? Transistor radios and televisions, and these were single transistors. Remember, we talked about how did a transistor become a semiconductor circuit? Well, if you take a bunch of transistors, resistors, capacitors, metal wires, you create an integrated circuit, and that gave birth to computing. And remember, it's not a single transistor. It's billions of transistors in a design, but hundreds of different types of transistors in a given circuit design. So this is what became of our industry. I call it the eras of compute. It started with centralized computing. We were connecting data to our projects or our applications. Then the birth of the PC came about, and we were able to do distributed data. We didn't have to run. We were talking at breakfast, Sandra and I, to professors here. When we first came to school here, you had to use the central computer. That's where everybody, and you had to book time on the computer to get your work done. And this is about the same time the PC industry started to come. Then we connected all these PCs, and we were able to share our data, not just calculate our own work. Then, of course, came across the internet and wireless computer, where we were able to connect with everybody everywhere. Then the birth of the smart mobile device, mobility came, connecting everywhere, which gave birth to the Internet of Things. Why would you have the Internet of Things if you didn't have something you could control in your hand? Now, the Internet of Things began with what I call kind of dumb devices. Your thermostat on the wall wasn't thinking, it was just connected, and if it was better to be able to change the temperature in the morning from your phone than to go wake up and go outside and turn up the heat. And then we moved to the age of smart connected things, where everything's connected. And we're going to talk about AI at the edge, where we take smart connected things and we AI enable them. So every one of these areas of compute had an economic value to our industry. And what you're looking at on the far left is the number of units that were deployed in these different areas of compute, starting with mainframe, mini computer, personal compute, smart mobile devices, and IoT edge. And what you're looking at is orders of magnitude of applications for every area of compute, from tens of thousands of mainframes to tens of millions or hundreds of millions of personal computing, to billions of smartphones, to tens of billions of IoT devices and edge devices. That has driven the economics of our industry. This has driven by Moore's law, but also the economics of the industry to afford Moore's law. And that's where our industry is today, at the forefront of IoT at the edge. But like every industry, in our State of the Union, we have two really important things we need to overcome. One is physical, in the resiliency challenged by concentration in our industry, and I'll talk about that in a moment, both geological and industrial concentration, and then Moore's law being challenged because the acceleration of complexity. In this world that you live in, complexity equals cost. If someone says something that's complex, just know you're getting a big bill for that. And complexity goes right against the first principle of Moore's law, which was an economic model of creating lower cost transistors to open up a whole new space of applications. So let's talk about the first one. I'm sorry, the first one being on the left. This is what I call the inverted triangle of how important semiconductors are in the world. You have a $104 trillion world economy that I would argue is supported by a $2.5 trillion electronics industry, with thousands and thousands of companies making products that use it. Now, that electronics industry only exists because of the electronics, which are the semiconductors. It's about a $500 billion business, hundreds of companies. And you'll recognize their names, the AMDs, the NVIDIAs, the Qualcomms, Texas Instruments, Samsung. By the way, let me ask a little audience participation. AMD, NVIDIA, Qualcomm, what do you think they manufacture? Anybody have an idea? What do they manufacture? Yes, sir.
The structure and organization of the chips that one, they end up creating what the AMD after that AMD.
Okay, you said the word manufacturer though. Go ahead. Yeah.
Just designer.
They don't manufacture. Exactly. They're designers. They're IP houses. They let others manufacture for them. Now, on that other list are companies that do both. We call them hybrid companies. An integrated device manufacturer, by the way, in the 80s, that's all there were. There was no such thing as fabless companies like the Qualcomms of the world. Fabless, they don't have a fabricator, so they send their designs out to be made by someone else. Foundries, who's only, and we'll get to them in a moment, that's where GF, Global Foundries plays. So they were integrated device manufacturers. They not only created their own products with design, but they also manufactured. There is no such thing, for example, in the world today of a pure play integrated device manufacturer. Think of one of the biggest ones, Intel. They're a customer of GlobalFoundries. They don't build everything they do for their products. They use TSMC as well as a supplier. So very few, most semiconductor companies are fabless and no pure play integrated device manufacturers, a few hybrid, like you'll see up there, Texas Instrument, Skyworks, they manufacture some of their products. Most of the time they come to GlobalFoundries to build their products. And then we come down to this foundry industry, the manufacturing, a little bit over $1 billion. Now, there's only 5 companies of any scale that are foundries across the world. I chose scale at $2 billion of revenue because to afford to make the investments of billions of dollars to create capacity, you need a certain level of scale. I think I'm being very gracious with a $2 billion clip level to say you can be a real foundry, given, GF last year was $7.4 billion. So a big threshold. We could take people, companies, a fraction of our size and call them foundries, and they just don't exist. Maybe the one that could almost make the list at $1.2 billion is Tower Jazz, another foundry. But listen to this, the world economy, $104 trillion world economy depends on 5 companies. So what do those 5 companies look like? Well, one is SMIC, and they're in China, and given geopolitical concerns and the proximity of SMIC to the central government, they're not a real option for many Western companies any longer. By the way, that will only get tougher as the rhetoric heats up between the geopolitical tensions in the world. You have UMC and TSMC, both in Taiwan. You have Samsung, who's got a division of the conglomerate company, foundry business. And then you have GlobalFoundries. All these foundries, other than TSMC, were all somewhere between $6 to $9 billion of foundry revenue. And last quarter we were better than UMC in revenue. Maybe this quarter they'll be a little bit higher than us. We're all roughly the same size. But here's the problem in our industry. Take the revenue of SMIC, add it to UMC, add it to Samsung, add it to GF, take the sum of that, multiply it by 2, and you're not as big as TSMC. TSMC is 10 times bigger than GlobalFoundries. Huge concentration in our industry in one company. By the way, 70 to 80% of all manufacturing and foundry is in Taiwan, both a geopolitical and geological area of interest. I can't imagine the founders of our industry 50, 60 years ago sat around and said, in 50 years, what would success look like in the semiconductor industry? Oh, I know. We'll concentrate 80% of the world's production on a small island in the ring of fire in the middle of geopolitical tension. Success. And this is an issue. And you say, well, how did we get this way? We got this way because of economics. Taiwan invested in a big way to create an industry with a lot of forethought and made it easier. And then the bigger the scale became, the better the competition in having the right cost position. And what I think is unconscionable are boards of hugely highly valued companies, trillion-dollar companies, multi-trillion-dollar companies that don't sit back and take stock and say, we need to do more on getting resiliency of supply. Because these companies can be destroyed overnight with any of these issues that create a supply chain disruption. And that's why supply chains are really important. It's about resiliency as much as access and low cost. And when you solve only to one boundary condition called cost, that's how you wind up with an issue like this. So what's the world doing about it? Well, look, GF's doing its part. In fact, one of the things that's a value proposition more and more to our customers is our global footprint. We have 2 facilities in the United States. In a town called Malta, New York, about 20 miles north of Albany, is our most advanced 300 millimeter facility. We have a 200 millimeter facility in Burlington, Vermont. We have a huge facility in Dresden, Germany, 300 millimeter. And then our largest facility by capacity and employers is in Singapore. Global diversity for our customers. You'll see a press release coming out soon about a key customer of ours. And one of the decisions to source from us on this very special and differentiated technology was the fact that we could build it for them both in Europe in Germany, satisfying the auto industry. So we need to do more of this. What are you seeing in response in governments around the world? Every country's got its version, or every area of the world's got its version of its CHIPS Act. The US has their CHIPS Act. By the way, CHIPS Act's 15% of the CapEx spending offset to create capacity, but the US also has an investment tax credit for 25%. So for every dollar you spend to create capacity in the US, 40 cents of that, the government will co-invest with you. European Union doing the same thing. Singapore's been doing that forever. That's why we have a big campus there. So the world is trying to respond by creating incentives that level the playing field and the competitiveness to create capacity in different regions of the world because of this concentration of supply. Even companies like TSMC are building factories in Europe and Arizona. Small fraction of their overall capacity, but it's a start because it's addressing the challenge I just spoke about. The second thing is Moore's Law is challenged by acceleration and complexity. I didn't have to say cost and cost. I should have just put an equal sign between the two. Let's take a look. In the 80s, when I was at Columbia, that was the elements on the periodic chart that came into semiconductors, 11 elements. By the 90s, we graduated to 15 elements, and now we're 60 or more elements. That means the complexity of building each layer of technology is higher and higher. We go from PVD to CVD to plasma enhanced CVD to atomic layer deposition to metal etch, dielectric etch, tons of different process steps to integrate these materials to get the desired size of transistors and functionality of transistors. Huge complexity add. What is it done by the numbers? You could see the number of process steps, the number of times a wafer has to move from one tool to another has doubled from 28 nanometer to 7 nanometer. This is over roughly the last decade. Maybe I can argue between 15 years for the leading capacity of 28 nanometer to today. And the same thing on photolithographic steps, right? From less than 50 mass steps to almost 100 mass steps to get the same level of technology or same level of product. Now, what has it done to cost? Not only is the cost of creating the semiconductor gone up, the cost of design and technology is 5x over a very short period of time since 16 nanometer, given the complexity of designs. So everything's costing more in our industry, but it's okay for things to cost more if you've gotten the value out of the technology. Well, look what's happened. The heyday of our industry from 86 to 2011, transistor density, which is that shrink factor of the transistor that gives the economic value, twice as many transistors in the same area, has really plateaued. And since 2015, we're talking about 3% a year. Cost is going up exponentially while value of the delivery has gone down. So what's the scorecard of Laws Moore look like today? Remember, it's an economic model. Well, first, are we getting low cost per transistor? No, we're not even getting flat. Transistor cost is going up. So you're not going to use a 3 nanometer, 5 nanometer transistor unless it has some value for you. Well, is it because of performance? I'm going to be an easy grader on this and lean in and say, yeah, maybe we're getting some device performance, a little extra speed. Most of the performance we're getting is through better designs and more efficient designs. But we are still getting low power per transistor. If we're shrinking, we get lower power. Why is that important? If you're running an AI data center, every transistor and the power it uses is important. One more question to the audience. Do you know the figure of merit used to talk about the size of the data center? What's the figure of merit? No, there's a figure. I'm going to build a data center and it's going to be X something. What is that? It's in megawatts or gigawatts. You would think a data center would talk about teraflops or some kind of compute figure of merit. It doesn't. Power is so important to data centers. You only talk about the size by the power it uses. I'm Google. I'm going to go build a 100 megawatt data center. Wow, that's big. That's why power is such a premium And it's the only reason people invest billions of dollars a year in R&D and tens of billions of dollars in capital deployment to do that next generation technology is for an application in a data center where high intensity digital compute is a premium. Well, so what does that mean? It means our industry cannot cover all the elements of what we need to deliver with Moore's Law alone. It's a necessary but insufficient part of our industry. For data centers, we need that type of compute. But for the rest of what we're trying to do, it's cost prohibitive. So we'll go and give another example of what other industries have done when they've hit a wall in their value proposition. Let's look at the airline industry. From the Wright brothers at about 60 to 70 miles an hour to the mid 80s, we went from 60 miles an hour to almost 2,200 miles an hour. But we hit a wall of the physics of flying. But the airline industry didn't say, well, we're done. They found other ways to create value, both in safety, fuel efficiency, aerodynamic design, airline scheduling, things where innovation, again, created the experience for what flight was all about. And what is our industry doing in response to this? We need to apply these same lessons to the semi industry because the end of Moore's Law is here. We're at this crossroad. There's migration of nodes. So you don't get the scaling effect, but you get the power we talked about. So there'll always be a certain level of applications requiring that. And the answer is what GF does. We call it platform innovations. We add features for specific market types to go and create the value, both the economic value of the right cost point and the technological and the features that we bring. So let's talk about what that looks like. For us, we think about the world as an automotive segment, a home and industrial IoT, smart mobile devices, communications infrastructure, data center, aerospace, defense, and critical infrastructure. Those are the end markets we target our R&D to. And we do it across the 6, we'll call product lines. Bulk CMOS, memory that's applied to all these platforms, ultra-low power CMOS, silicon photonics, RF, and power. By the way, some of you probably use GF's PDKs to do some of your designs and turn them into experiments into actually seeing your designs in physical silicon. Anybody here on a GF shuttle? There you go. Be proud. Come on, right up. So I'm not going to read this chart to you. I'm going to give you a great example. If you have a smart mobile device, an iPhone, just pick it up in the air. Okay. All right. How many of you use Apple Pay? Well, we make the chip that does that. What does it combine? It's got some digital analog content. It's got great NFC, near field connection. The most important thing, it has embedded memory that's secure, so the secure element doesn't give away your credit card information. How many of you like the touch screen on your phones? You're welcome again. We make the chips that do that. Do you like the battery life of your batteries? Power management ICs, that's our specialty. How about, do you connect your phone to cell towers for internet and phones? You can't find a smartphone by any manufacturer anywhere in the world, any label that doesn't have GF content in the front end module, switches, filters, low noise amplifiers, power amplifiers, the integration of that stuff, that's a GF franchise. And my last one is you take pictures with your camera, the image sensor processor is built on our technology as well. These are all feature enhanced technology nodes that are 12 nanometer and larger in transistor size, but hugely featurized to create the applications at the right performance and cost point. That's what we call platform technology innovation. That's where we pivoted our company to go after 60% of the market, not 40% in the high-speed digital compute. So what's next for our industry? This is the big finish. And it's really about the mega trends in the world. It's about digitalization, connectivity, and cloud. Digitalization. We live in an analog world. Everything we're doing. What I'm doing right now is analog, and everything needs to be digitalized. Well, then we need to connect that digital content to some place. Typically, it's where we could store it in one place, to the cloud. And it's these 3 mega trends, when they come together, is really what's powering the rise of AI. How these 3 trends come together. I like to think of it as a virtual cycle. It's fueled by intelligence at the edge. It's accelerated by connectivity. It's enabled by the large language models in the cloud. We are a technology industry, but we're led by economics. The data centers you're seeing built out today, that party will end at some point. Right now, it's a race to, well, if I'm a hyperscaler and I don't have all this compute power, I may be left behind, not sure how to use it. The problem is the data centers will run out of data to do their large language models. And this concept of, well, we can synthesize data for our models, maybe one iteration it works, but over time it becomes contaminated. So where's the data going to come from? It's going to come from the edge. And this is how we see the world of AI. It starts with the edge, where off means off. What does that mean? By and large, any IoT device, certainly an AI-enabled device, sits in the standby state. Think of a Blink camera or a Ring doorbell camera. Most of the time, it's idle. It's waiting for something. And many times, it's not even tethered to a power source. It's on batteries. So the biggest attribute from a transistor performance is when it's in that off state, that standby state, it uses 0 to no power. That's where GF has invested a big part of our R&D to make sure that we have the lowest power when a device is in the standby mode. So what does a Blink camera do? Every 10 milliseconds of every second, a microcontroller wakes up and sees if something's going around. If it doesn't, it goes back to sleep, whatever a second minus 10 milliseconds is. So a very small fraction. If it sees something, it wakes up a bigger microcontroller and then takes the action. By the way, over time, it won't just, respond to someone ringing a doorbell. It'll be sending you a signal. Tom's at the door. Do you want to let him know you're home or not, right? But that's how these edge devices will work in the future. They're very power sensitive in the standby state. The second thing is you need precision analog. Everything about what happens at the edge is analog that needs to be converted into digital. The better the fidelity of that analog conversion to digital, the better the signal, the better the data set is for you. Inference, parsing, and compression, that's what's going to take place at the edge. The large language models will be deployed at the edge device, so inferencing takes place. Now, that's when I walk up to the doorbell and the inference decides what it's going to do with that sensing. Now, it just sensed something and it takes an action, but that data now is still very valuable. It needs to be parsed and compressed and sent to the cloud, which talks about why we need connectivity. The fuel of the AI revolution will be at the edge where all the action is, where all the data is being collected and acted upon. So what do we need? We need integrated RF at the lowest possible power. Power is going to become the new economic model for our industry. We need fast switching at low losses, and we need highly efficient millimeter wave because we're going from 5 to 6 gigahertz to 27 to 36 gigahertz. We get bandwidth and speed and performance. So that's what happens at connectivity. And then what do we need in the data center? Well, we have to eliminate the bottlenecks. Electrons are not cutting it anymore. For interconnectivity, we need to convert electrons to photons. Remember, photons don't see each other in a waveguide. So you increase bandwidth and capability by orders of magnitude. We need high-speed networking and efficient power delivery. This is when I was going to ask the question of how data centers are described today. Power is everything in the data center. In fact, what's going to limit data center build out is access to power. Who's going to allow you to build a data center in a town where the grid can't support that level of power usage? And so for GF, that means integrated voltage regulators and technologies that allow better power efficiency in the data center. And how does it come together? The AI opportunity ahead, the edge is where the full potential of AI is going to happen. It's not going to be in the data center. Data center is necessary, but insufficient. It's going to drive a replacement cycle. Every device we have, and it started with Apple this year saying their new iPhone is AI enabled. Every device we have today, over the course of the next 5 years, will be obsolete because it won't be AI enabled. You'll need a refresh cycle. which will drive our industry to growth again. And by the way, the most important thing, at least from GF, it requires what we call essential chips, feature-rich chips, chips where innovation is beyond Moore's law scaling. And that's the future of our industry, how it's going to enable AI. I think that's my my last chart for Q&A. How did I do in time? Is this where we stare at each other for 20 minutes? Or? Oh, okay.
So what actually does resilience and supply fully look like in your opinion? Oh, yeah.
In case my voice wasn't loud enough already, yeah. So what does resilience to supply look like in your opinion with regards to, there's 5 major producers, as you said, of chips. You're one of them. Does that look like as somebody actually trying to be able to make 7 and 3 nanometer chips that TSMC now has a monopoly on?
So I think there's 2 elements to it. There's geographical resilience, because you need to spread the risk around the world. You can't have a supply chain. You can have hurricane. You can have all kinds of natural elements that we don't even get to, call the shot of. In our industry, it also requires diversity of technology. Today, only one company can reliably build 5, 4, 3 nanometer technology. It's TSMC. And they do it in Taiwan. They're going to bring some of that over to the US. We need diversity of companies that could do that as well, because you just need that competitive balance. And this is why the US government wants to make a big bet and try to help Intel get their mojo back. But to date, they've been struggling doing that. So we need it geographically to have diverse footprint, and we need it for technology purposes.
I have a question. When you're gonna go from electrons to photons, you have to be careful because photons have which kind of spectrum of photons are you gonna use? Because you have to take into the consideration the health effects.
Yeah, so I mean, right now, the technology is all just beyond the visible spectrum. 1250 nanometers. Who's a photonics engineer? 1250? 1550 and above. That's the wavelength photonics is using.
So you're gonna use the visible spectrum?
What?
Which photon spectrum? Which wavelength?
1550 nanometers.
Nano?
Yeah.
Okay, thank you.
So it's brilliant. It's a brilliant talk. Absolutely impressive. So I have a question about kind of like 2 things that I see that you mentioned in your talk. First is that I see in your chart in the technology you have mentioned around like 3 times around silicon photonics. And then also in the end, when you talk about that infinite sign, the right side of the infinite sign, you talk about electro to optic conversion as a kind of your push. And then I want to just add the context, because I think one concept you mentioned in talk is, which I find completely inspiring, is that we are near the edge of how we can conventionally scale our performance. We cannot like hone the knife any more sharper. So we need new approaches. So what I would wonder is, in terms of kind of integrated photonics, would you agree in this sense that right now we are at kind of the eve before the Shockley moment in photonics?
Yeah, look, photonics has been for the last decade right around the corner, but there are boundaries, and I think it's just going to be 200 megabytes per second, that there's no choice to stay with copper. One of the things we have done to eliminate the challenges of the integration is we've made a monolithic solution where we integrate CMOS, RF, and RF-SOI into a single chip. It's more complex, but it's better to put the complexity into the chip than to put the complexity into a broad set of heterogeneous and homogeneous packaging. So we think we'll get to the market fastest by having a simpler solution for the integration. Now, part of Moore's laws challenge in how we're going to continue to innovate beyond that is going to be through chiplet designs, through mixed technologies that get integrated at the package level, both heterogeneous, homogeneously, wafer bonding through silicon vias. These are all the next tricks for the industry for how to get that level of integration at the right cost point. And it's not going to be trying to add, embedded memory or RF to 3-nanometer technology.
Hello. I was just thinking, I saw you're doing a lot of manufacturing in Asia, for example, America and also in Europe. And there's currently a tech boom happening in Africa. So I was wondering, are you thinking of investing in Africa or possibly manufacturing within the African space?
Yeah, so this is the big push by all governments around the world. If we think the future of the economy for economic supply security, national security, and supply chain security is you need to have semiconductors in your region. Everybody wants it. India is making a big push. I think India is a proxy for what will need to happen in Africa. The infrastructure, the reliability of access to water and high quality power, that infrastructure needs to be in place first before you do manufacturing. Now, that's not where you have to start. You could start with packaging. You could start with introducing the semiconductor industry through design, leveraging talent and education. And that's how it all builds up in these different regions. It never starts with a factory just grows up one day. It starts with an ecosystem that supports products to where there's enough scale where then it's worthy of manufacturing, where you can have manufacturing at the right scale and the right economics with the right infrastructure. That young lady right there had her hands up, Paul.
Thank you. I had a question. I wanted you to talk more about the security and privacy of this data, especially with the rise of the data collection, as you were mentioning.
Yeah, well, a big part for us is to make sure that our technology is not hacked. But in the products that goes in and the software that controls that, we have no say in it. So it's important, like when I talk about whether it's the card we make for the credit card or for Apple Pay, is to make sure that what we do in that isn't vulnerable to hacking and attacks. But the applications that use chips at all those different levels above us, that's where your vulnerabilities are, not at the semiconductor level. I worry about chips made in parts of this world where part of the business model is to steal technology and information. Can those chips become compromised, and how would we test for that? Or
The scalability and the data centers, and this is an area that I think some people might be worried about.
yeah, I envision a world someday where the safety warning on your electronic device has to validate where the chips were manufactured for security purposes. I think we're a decade away from that, but I think we need a couple of really bad examples of why that's important to create that kind of, it's always going to be that way, right? The warning labels on cigarette packs didn't start until there was enough deaths, right? Oh, yeah.
I'm next. Thomas, fantastic talk. Thank you for sharing that.
I bet you say that to all the speakers.
Your presentation focused on this incredible investment of semiconductor technology led by industry, fueled by industry. We're at a university. How can we at universities help this process? What can we do to help?
You use the word fuel. The brains are the fuel of our industry. Anybody with a checkbook and a desire can buy tools, can create a clean room. It's the intellectual power of the engineers we train here. That's the fuel of our
But
industry.
just a follow-up. To get that intellectual power, we need experience, hands-on operation at the levels at the industry. And at our campuses, how can we begin to interact or collaborate with facilities?
Yeah, I may be a little bit different on this one. Given the specificity of what we do, is a big part of our onboarding of our technical team that's about training in-house that you can't replicate on campus. You want to create the best opportunity, make the best engineers on the fundamentals. We'll take care of the rest. I don't care if they don't know how to put a bunny suit on. In a day, they'll learn how to do that. And so I worry less about the specificity of the vocation and being too narrow. Give us educated both on liberal arts and science and engineering, and we'll take care of the rest and make them semiconductor professionals. That's how I view it. By the way, Global Foundries, last November, we announced it. It came into effect in May. Not only do we do tuition reimbursement for people who want to go back to school, we do debt relief up to $28,500. So if you come in with student debt, $2,500 a year, tax-free, comes from us to pay off your student debt. If you're looking for a career and you happen to bring a little bit of student debt with you into your.
That's right.
How to get that out there. Resumes can be collected on the back.
This is just a follow-on to the prior question, actually. In terms of the lull that has happened in the manufacturing side, there's a lot been going on in terms of NSF and other grants trying to develop workforce development, like Nortech is tied to that, but that Department of Defense. So it's tied to Columbia and the research side, but just in terms of real good jobs for people, economic development, how do you see that coming about through CHIPS Act and manufacturing?
So this is the big thing about manufacturing. More than half of those jobs are for non-college educated. They're technicians. They're people that get a technical 2-year degree. And the one thing about manufacturing you're not going to get in any other part of our industry is that everybody gets to participate in the economy. And so for us, we spend as much time training at local community colleges and BOCES type schools to create those that workforce development, by the way, who have every opportunity to advance themselves into engineering through the programs we create if they so choose. So I think the thing about manufacturing that's different than anything else is it creates a broader spectrum of the social economic participation in the industry. I think we hear a lot about where's all this workforce going to come from. I think the semiconductor industry has to do a better job at marketing itself. Everything that we do and every piece of electronics you have, we're responsible for, but no one knows it. It wasn't until 2021, when there weren't enough chips, that everybody wanted to know where this happened. I cannot tell you how many calls with CEOs, whether it's iRobot or a car company, had no idea who Global Foundries was, who would have failed to question, what does Qualcomm manufacture, right? Until they couldn't get enough chips and asked Qualcomm, can I see your factories? And they said, oh, we don't have any. Let me introduce you to Tom. And so we created awareness because of short supply. We need to do better than that. We need to make sure that the most exciting careers in the next decade are in the semiconductor industry, not in what's been co-opted by software companies and cloud companies and maybe some of the product companies. That was an advertisement. Yeah, thank you.
Hi,
He's got the mic.
Thanks for being here. I'm Flavio. I wanted to ask you if you see we go back to IDMs or more vertical integration due to resiliency concerns or geographical concerns, or if you see this layering being more and more consolidated.
There's a balance between two things. I think right now the economics of our ecosystem are at a balance where value creation doesn't equal value capture. I think IP companies capture more of the value than manufacturing companies, but I also see that changing over time. So first, you need that balance. The second thing is, if you look at what the R&D budgets are just to be a design company, plus the R&D to be a manufacturing company, there's a reason the industry bifurcated into foundry fabless, even though it created stacked margins, right? I make something, I have to margin it up to make a profit, pass it to a fabless company, they have to margin it up. So the economics of the complexity of our industry have allowed for this bifurcation or segmentation. The real answer to your question is, will the economics turn where it's no longer able to have this, everybody gets to margin up, and then it will drive a reintegration. So it's not because of technology. It's always going to be because of the economics.
Hi. Thank you so much for coming today. I'm really grateful to hear you
You
speak.
guys are very polite. I
Um,
hope
you-
I was that way when I was here.
Undoubtedly.
It was, thank you.
You've spoken a lot about the output of how power is a focus, of course, of semiconductors in order to scale the resource efficiency, right, in data centers and beyond, and phones, whatever it might be. You haven't so much talked about necessarily the input, though, that makes the impact lower of semiconductors. And we know that supply chain resiliency, climate change, et cetera, is impacting our access to things like mining and the other raw resources that go into our semiconductors. So my question for you is, how else are you modeling the impact of the inputs?
So I'm not rephrasing your question, but make sure I have it. You know, the semiconductor industry has an obligation as well on what they're doing about sustainability.
Right.
So you can't get around the fact that, you know, any one of our fabs uses somewhere between 100 to 130 megawatts of power, right? But we have to make investments to offset that. And by the way, what about the things, the effluents that we give off? In fact, just recently on LinkedIn, you could take a look at what we just posted. You know, we're investing $75 million over the next 3 years to do more of this abatement, to sign up for power, you know, PPAs, the power offtake agreements for more green energy. We're going to cut our carbon footprint by 50% while we grow almost double between now and 2030. We've taken it, I would say, maybe not as ambitious as a pledge as maybe we could have, but by 2050, we will be carbon neutral. A lot of it has to do with what we don't control, and we need innovation. If we need electrical power, short of us building our own nuclear power plant, how are we going to go do some of this stuff? But we're very, as an industry and as a company, very focused on doing our part on that.
Maybe I'll just ask though, but it goes beyond power, right? Because it goes into water and biodiversity effects and how those.
Reused water, right? You know,
Right.
how much of our water is reused, right? Most of it is for cooling.
Right.
So it gets recycled through. It may not be potable water any longer, but we do that. You know, I will tell you, if you're interested in that, I would send down our environmental executive to talk about all the things not only GF is doing, but the industry is doing. Yeah. Are you an environmental engineer? Are you looking for a summer job? Well, why don't you come learn about that? Serious. Okay.
Thank you for the talk. One aspect is with the physical limitation of Moore's law, where you can't really kind of create more chips physically. Other aspect being considered is quantum computing, and that kind of taking it out to the next curve from a computing perspective. So as you look at it, do you see a role for global foundries in this, and how do you see that industry develop? I again understand that's very early days for that, and a lot of research continues to happen. But will that start replacing some of the kind of major computing challenges?
Yeah. So, you know, what's the role of quantum computing? It's not going to be in your iPhone, but it's a way of creating the same value proposition with the same amount of transistors. Now, I'm very biased towards quantum computing. It's a decade away, and it's never going to work on matter-based technology. It's not going to work with electrons, and it's only going to work with photons to get the millions of qubits you need to make something that's functional. So while there are big companies that have done silly pet tricks and said we did this computation with 100 qubits, it's nice because it builds buzz around it. But the only way a quantum compute ever sees commercial success is through photonics. And you're right, there's a way of offsetting some of the losing Moore's law by doing a completely different architecture for how compute is done. but it's not going to be pervasively deployed in every device that we have. Very opinionated guy. Right here.
Yeah, sure. So, thank you. Thanks for the talk. So, you're talking about like a semiconductor as a leveraging platform for many applications. One of the applications that over the last 10, 15 years, just like surging is using a semiconductor for biotech or biology, and then bringing the biology interface of like a semiconductor. So you can see like in sequencers or biosensors, everything is just expanding. So what is your strategy? I mean, do you have anything that in this domain, or do you have companies that using your foundries just developing like technologies for life sciences?
It's a great question. You know, for GF in 2020, so in 2018, when I became CEO and we pivoted away from trying to chase Moore's law to what we call feature-rich technology, the things we talked about, we looked at the automotive industry as a huge opportunity for us. In 2020, we had $90 million of revenue. And between then and last year, we grew it to over $1 billion. So we focused on the innovations required for that. We're beginning that journey in biotech and in the pharmaceutical. And it really starts with the integration of some kind of sensing of a fluid or vapor, and incorporating in that the analog and digital content to go and do something with that. And it's all back to the economics. If you could put enough content into something, and especially if it's reusable, then you can make large volumes. And that will start out, I think, mostly at 200 millimeter type production capability, because you don't need the finer features, but it'll only grow. So we view it as a big market opportunity for us.
Thank you for your talk. It's just a question that you mentioned about the cost of manufacturing keep going on in the edge of the Moore's law. So how would you see the profitability of the manufacturing industry, also the chip design industry, if these costs keep going on?
It's all about scale. So how does TSMC, who's going to spend $32 billion of capital deployment for next generation technology, make money doing that? Well, they sell a wafer to NVIDIA for $30,000 a wafer, who then takes that wafer and more than triples the profit they make off it, right? So the economics are still working on that end. The design is all about scale. There's a reason why fabless companies exist today. They exist very similar to how the foundry industry started with Morris Chang in the 80s. When you were in IDM, so why did IDMs these integrated device manufacturers cease to exist? Because the cost to build factories and the scale required exceeded the volumes companies had. And this guy, Morris Chang, came along and said, you know what? Let me be your great aggregator. You don't have to manufacture. I'll take all your demands of your products and I'll build them for you, and you'll get the economies of scale. Little did he know, he actually created the fabless industry, because a design that costs $400 million to do, if you don't have enough volumes, you'll never get the return on it. So fabless companies became aggregators of demand. I'll make a microcontroller for all cars. Each car company can't afford to have their own microcontroller. But if I aggregate all the demands from all the car companies, and that's how we got this segmentation of the industry. Our industry's economics always come back home to roost at scale. And that's what it will take.
So I believe the trend gonna continue.
Yes. Right here? Don't you guys have class?
One more question. We'll do one more.
Yeah.
Finally got the mic. Thank you so much, Tom. My name is Tina, and I'm a senior here. My question is, I'm curious to hear your thoughts on potential opportunities for industry consolidation, whether in a vertical sense or horizontal sense, and whether GF has an overarching thesis on where you should expand to inorganically.
Well, there's things I can't talk about, or they put me in an orange jacket. But look, the industry has been about consolidations because scale matters. And the best way to get scale is to bolt things together and create. That's how Broadcom started, is this little Avago, and Hock went and bought every company. Now, what happens is, like any good thing, it becomes a problem where you can't grow through consolidations, whether you're creating anti-competitive dynamics, or you have geopolitical edge that don't let deals come through. There was a ripe time for consolidations in our industry between 2005 and say 2015. Very tough to do that. Does Tom Caulfield think the semiconductor industry needs more consolidation to be viable? Absolutely, because we're starting to lose in scale. I gave you the example. TSMC is 10 times the size of GlobalFoundries and twice the size of the combined revenue of the next four. That's an area where consolidations need to happen to create some of that balance. The question is, can they happen geopolitically? Do they make the right cultural sense between companies? But the industry needs consolidations. It's always been part of the creating the scale to continue to make competitive companies.
All right, I think with that, we do have students need to go to class, but the question is really so amazing, right? Education, right? Market economics, sustainability, university. So I want to thank Tom and Sandra here. I'm sure if any questions, send it to us, to them. Let's thank them for their.